You gotta wait for recording. Okay, hello everyone. My name is Beth Mashesky. I am Senior Scientific Specialist at the Illinois Sustainable Technology Center and seminar co-organizer. Our next seminar will be on April 26th at noon at ISCC. Carter O'Brien, Sustainability Officer from Chicago's Field Museum of Natural History, will be presenting From Landfill to Lead, Institutionalizing Sustainability at Chicago's Field Museum of Natural History. I'd like to remind those in our audience to please silence electronic devices as we are recording today's seminar. We will hold all questions until the end of the presentation. Also, for those online, you can type in your questions at any time and we'll address those at the end as well. So with that, I'm very pleased to welcome today's speaker, Jane Frankenberger. Jane is professor in agricultural and biological engineering at Purdue University. Her research focuses on agricultural watershed management and developing drainage and agricultural water management strategies to reduce nutrient losses from subsurface drained lands. Please join me in welcoming Jane.
Thank you. I'm so pleased to be here and see a good group here. I know it's spring break here at Illinois, so great to see people here and find out a little bit about this institute. I really appreciate you inviting me. So, right, the key words here are drained agricultural landscapes and thinking about resiliency. Resiliency is a word we're thinking of all kinds of environments today, and so we'll talk about what we mean here. I do want to say right away that many of these slides and illustrations come from grad students, as so often is the case of them along the way. As I assume you all know, but I'm going to start a little bit with the background of why we have drained landscapes. Obviously, people are very concerned about getting rid of excess water, and we have good strategies for doing so. So I'm going to start with, instead of just showing photos, showing a little bit of a video, because I happen to have it, of drainage being installed. So this is the only time that you really see the drainage. You probably know that it's under a good chunk of our agricultural land, 50% in Indiana. I don't know the percentage in Illinois of what we're guessing, but it's probably more than 50% actually. So there is a lot of it. So the white is perforated plastic tubing. This is one of the drain plows that's installing it at about 3 feet deep is where it typically is. This was taken by a drone at a field day last summer, having a field day with a lot of drain plows there. But it gives you a sense, I think, of how fast it's going in. Some of them, they lay out the drain tile along the way before it, and some of them are actually holding the rolls. But obviously, millions of feet are going in the ground all the time. So I just wanted to start that way in case anyone is unaware of this unseen plumbing system, really, that underlays such a lot of our landscapes in the Midwest. Okay, so we have this infrastructure. I think more and more people are using the term infrastructure because it really is something that sits there and provides all kinds of benefits, works all the time. It's extensive, it's efficient, and one thing to remember is it removes water all year round. So it consists of the subsurface tile drainage, which is what we just saw being installed, and then also the surface drainage. A lot of ditches that these subsurface or tile drains, as people usually call them, flow into the ditches, and then of course they serve some drainage purpose as well. So this is the part of the system that you see sometimes. It's in a nice straight line, which I think is how they are in Illinois too. They line those up really nice when they put them in 100 to 120 years ago, something like that. So, but there are issues. And again, they probably are aware of this, that all is not well in the world of having this drainage system. And the first one is the nutrient losses. It's been known for a long time, as long as I've been in this job, that nitrate coming from the tile drains is the major source. It's the major flow path for nitrate that gets into our streams, into our rivers, and into the Mississippi River and the Gulf of Mexico. Because so much flows right down through the soil, picks up the nitrate, which is highly mobile, and comes out in the tile drain. So sometimes, not you, but sometimes farmers say to me, it's clean. I can see that it's clean, but nitrate is obviously invisible. What's not been really talked about for so long is that it's also an important flow path for phosphorus. And I encounter people all the time that say the major loss pathway for non-point source phosphorus is erosion that comes from the slopes and it's absorbed to soil. That is an older way of thinking, and if there is a lot of erosion, it can carry a lot of phosphorus. But in our very flat, very low erosion kind of soils, a fairly large part of the phosphorus can come through the tiles. This will vary by system. Over in the Lake Erie Basin, where I'm sure you know they've had such terrible problems with the algae and toxins from the algae due to phosphorus that's coming through, it's been shown pretty clearly that at least half the phosphorus is coming through drain tiles. So it's not maybe the majority, and in Illinois it's probably less than that. But still, we can't go with that old wisdom of phosphorus goes over the surface, nitrate goes through the drain tiles. They both come through the drain tiles. So that's an issue of what we have today. So when I go out and speak with farmers, you know, people understand that, they accept that. It's not a terribly popular message, but that's what we bring to them. The other issue that people are just starting to think about more now is the issue that even though we have way too much water in the spring, and people are really focused on getting rid of it, right? That's why millions of dollars are being spent getting a better drainage. In fact, our crop yields are probably limited in at least half the years by lack of water. So right at the late summer, July, August, when corn, for example, is silking and needs a particular amount of water, there's often not quite enough, not always, but in reasonable number of years. This is an Indiana kind of slide, but one indicator of that is the fact that crop insurance in 25 years in Indiana, they have paid out $930 million for flooding or excess moisture. They paid out $1.6 billion for drought, and I suspect it might be somewhat the same here. So it just kind of reminds people that, okay, we think about excess water, it's there, it's a big problem, flooding is a big problem, but drought is an issue too. And in more and more years, we see both of these in the same year. Now, this is getting a little old because I've been talking about 2015 for a while, but it was very striking, and often farmers remember this. We had terrible flooding in June, and then in the same year, it completely stopped, and we had land that was much too dry. So these are not different years, wet years versus dry years. It's the extremes, even within a year. And as I'm sure you know, but both of these issues are expected to be exacerbated with the changes in the climate. So the springtime, when we have a lot of drainage and we have nutrients coming out, that's when it's getting wetter, right? And the evidence is very clear that this has already gotten wetter, and the models show that it will continue to get wetter in the spring. In the summer around here, it's not necessarily getting drier. There isn't necessarily less precipitation, I should say that. But it is getting drier because of two reasons. One, as it's getting warmer, even if you have the same amount of precipitation, you have more evapotranspiration. So it's drier because of that. The other reason is more and more of our rainfall is coming in very flashy events, very intense. And those are the ones that are not necessarily infiltrating into the soil. So in fact, our soil becomes drier in future years as we look our way up. So the two problems are already there, and they're getting worse. Thus, we start to think about resilience, right? So that's one of the ways that resilience is often used. So the obvious solution, this is not very creative research to come up with it, but whenever you have sometimes too much of something and sometimes too little of something, you think storage, right? We've done this for a long time. So, but the question is that a lot of, and I'll tell you about all the people that are thinking about this across the Midwest, are thinking about how can we start to actually store drained water in the landscape to increase our resilience. And there's a project called Transforming Drainage that I'll come back to. I'll just mention that Ruth Book, the state NRC of engineers on our advisory committee, it's a big project. I'll talk a little bit about it at the end. So back to how this fits in with current drainage, right? Almost anyone who is managing drainage now has a single goal in mind, and that's how fast can we get rid of the water, right? And so we're getting rid of it as fast as we can. It's not obvious at all that we would be able to store water in our intensively used agricultural landscape. But that's what we're starting to put our heads together. Are there ways to do it? So a lot of what I'm presenting today is by no means finished research, but hopefully that's, it's a seminar. So we're sort of throwing out the ideas. And this is what I do with farmers all across the Midwest, and sort of helping people to envision how we could do more. And there are more and more people that are saying, yes, we can do something differently than just getting rid of the water. So this is a typical drained tile. Okay, so here's the tile drain. We've got the field. So can we store water in the field? Maybe. Can we store water in the buffer? That's what we got, maybe. In the ditch, so where, we're just looking in our landscapes, where can we actually store some water? The first thing I always start with is the idea of soil health. This is very big in the world of conservation these days. Almost everybody's talking about conservation is talking about soil health, and the fact that this can increase the storage, the water storage in the soil a little. So I'd say it's absolutely true. It's directionally clear. It's not going to decrease it. It's going to increase it. There's no good data on how much it does, and in our already excellent soils, it probably won't increase it all that much. These are not the degraded soils that really desperately need better soil health. We already have excellent soil health, but probably it can get some more water storage. Other people are looking at how we can change the ditch system. Can we, instead of just using them as conveyance structures, can we actually store some water there? So two-stage ditches, I don't know if there have been any or many in Illinois, but the idea here is that you bring back the banks so that there are benches where, first of all, it's wider, so a lot more water can be stored here, but also it can interact with the bench and have more nutrient cycling that way. It increases denitrification there, but it is also a storage practice. So some of the public drain managers, different in each state, I think you have drainage districts here, they like this idea because they can address flooding a little bit, because some of it can be stored. When you go downstream and you have a culvert somewhere, that acts as a dam and you really are storing it there. Another practice that they're pushing a lot in Iowa, it's not that practical in Indiana or Illinois, in most places, but there might be a few. So we mention it, and maybe as people hear about it, they say, okay, I've got a place. But in this one, so we have buffers on a lot of our streams and ditches. I assume you do here. But when we have when we have a drain going under the buffer, this buffer has no function as far as water quality, right? Nothing is happening. So what people started thinking is we can put a control structure in at the top edge of the buffer if the land is sloped, right? We can put a control structure and then distribute the water and the nitrate back into the buffer. Now, what does that do? If you take it out of the tile line and put it into the soil under the buffer, well, it allows that water to interact with good soil, and therefore denitrification can take place. So it's the nutrient cycling that can come about if there is high organic matter and saturated soil, which you can get them at. The problem in a lot of our very flat lands, which there's plenty of here, is this isn't any lower than the field. So if you saturate the buffer, you've saturated the field, and who wants that? So that really is the point. So it's a good practice for the few places that it works. So we're looking at that. So when you saturate it, then denitrification happens, which is a great way to treat our nitrogen. The next practice is another way to actually store water in the field, besides just looking at the soil. And this is a practice called controlled drainage. And here you actually put a water control structure like that in the tile drain at the edge of the field, not the buffer. And then when you don't need, before planting or harvest, obviously you need it. After harvest during the winter, it doesn't matter if you drain it or not, right? That's the flaw of our current system. There's no management there. So nobody cares if the fields are drained in the winter. They just are drained in the winter because there's no control at all. And so it's the obvious place that we can hold some water back, potentially increasing denitrification and potentially sending it through different flow paths that would increase the denitrification in different places. So controlled drainage is one that has been looked at in various places. The other reason that some farmers like it is after planting, you can raise up the water and potentially store a little bit in the field that the crop can use. And so that can address that problem I talked about at the beginning when there isn't enough water in the soil. So a little animation, just for those of you where maybe this doesn't make sense. The rain comes down, the way, the water table rises, and it holds the water back in front of this drain, right? So this is the water control structure is acting as a dam, not a valve, because the excess water will still flow over it, but it holds some of the water up. So I'm going to talk a little bit about, really, this project is finished. Controlled drainage research that we've had in Indiana at a place called the Davis Purdue Agriculture Center in Indiana. This is a picture when we were installing it in 2004, but we just decommissioned it now. So it's a 40-acre field with two quadrants that have controlled drainage and two quadrants that just have free drainage. So we have a little bit of replication I will just apologize here that, as you can see, I give a lot of talks to Extension. That's my primary audience, so a lot of my units are English units. Hopefully you're conversant in that. But when you talk to scientific audiences, I told me last night, like, oh, I should have remade all these slides with metric units. So sorry, that's why. Okay, so we have for 10 years been, 11 years in fact, been measuring drain flow into those four quadrants, the nitrate concentration, phosphorus concentrations in just 4 of the years. And now we finally have the results together. So the paper on this is in its second review, and I think it will be accepted very soon. So this is what we have found over the time. So if we look over the 10 years, I'm starting out by not going year by year, but aggregating the 10 years, but looking at the months just to get the patterns. So the free drainage concentration, this is nitrate N concentration, milligrams per liter. So January through December, this is in the free draining quadrant, and this is the controlled drainage quadrant. So each of these are average of a lot of years. We're taking concentration samples roughly weekly, sometimes a little more, sometimes a little less. So those are the average concentrations. So as you can kind of see here, there's no significant difference between them over the years. So it confirms what many other people have said as well, that controlled drainage doesn't change the concentration, but as you'll see in a minute, it does change the flow. So our average concentration of 8 milligrams per liter is lower than what a lot of other sites find. I don't know what all it's due to. This is a Purdue research farm, maybe managing things a little more carefully. Also, so as you go west, there's often higher concentrations. There's many places, if you get over to Iowa, where the average concentration would be more like 15 or 20 milligrams per liter, but ours is a little under that. But it did significantly reduce the drain flow. So this is just a portion of a graph that Samani Sadat has just put together. And hopefully you can see just with these years of how it works. So the gold part are when we're letting it drain freely. There's no control. So during March and before harvest. So it's the 2 times of the year that you need to have it free draining. And then there's 2 quadrants that are always free draining. So if we look at this year, let's look at this year. This is a good example. Okay, so during these free draining parts, we're getting this, 100 millimeters out of both of them. So there's 2 free drainage quadrants, there's 2 controlled drainage quadrants. When the controlled periods are, we get much more in the free draining tiles than the controlled drainage quadrants. So hopefully that just shows it, or sort of a sense of why the monitoring is tricky as well, because you're monitoring different things. You've got control periods and not controlled periods, but you've got to show that overall it makes a difference. But what we have there's many more years than that. The difference comes in the spring. So this is back to the 10-year average. The free drainage is here and the controlled drainage is here. So the reduction in flow is in the spring when we're holding drain flow back. And anywhere that does controlled drainage, you typically have 2 different levels. There's a higher outlet, I guess I don't have the numbers here, but usually maybe a foot from the surface during the winter when you're not worried about crop growth, and then a lower outlet level when you are worrying about crop growth during the summer. So then you would have it maybe 2 feet from the surface, something like that. And then the nitrate load, the thing that we care about, which is how much is going downstream, obviously is dependent on that. So in the free draining quadrant, we lost an average of 26 pounds per acre. Hopefully you know that kilograms per hectare are like roughly equal, so that about how much we lost. And in the controlled, 17 pounds per acre, making a 35% nitrate load reduction. So is that pretty good? You know, some of you probably know that the nutrient reduction strategies ask each state to reduce nitrate loads by 45% to solve the hypoxia problem. So even if we put something like this on every acre of the Midwest, we wouldn't get it down 45%. So that's one kind of drawback. And you know, there are other issues that this does take work because you're moving it up during sometimes and you have to move it down. So I think that's a real drawback of this practice, unfortunately. But it is a tool in the toolbox, right? And that's what most of us are just trying to find, different tools so we can suggest things to farmers that will make some kind of change. Think about that one. Phosphorus, we just measured it the last 4 years, and so what we found was it wasn't significantly different in the free or the control. So basically no difference, no impact there. We'll see about that. The crop yield is where people are hopeful. You know, could this practice pay for itself if the crop yield increase is enough? And some people are hoping that it is. Okay, so we've got corn for 9 years here. We've got soybeans for 4 years. I'm not showing the soybean years here. And so, like most of our agricultural research these days, we're using yield monitor data and removing the end rows. And here are just points that we can actually use. The yield goes from less than 80 to 200. This is one example here, but we've got a lot of years of this. We haven't published this yet, but it's about ready to submit different grants. So the yield that we have figured out is here. The average over all the years of corn, right? So this is not every year that we grow corn, 2010, 12, 14, 16, the other years are soybeans. In the free drainage quadrants, it averaged 157 bushels per acre, so not really, really high yielding. And in the controlled drainage, it was 162 bushels per acre for a 5 bushel per acre increase. Most farmers will say that's terrific. That if we could be really relatively assured of that, that would pay a lot because that's sheer profit. Obviously, the problem is it goes up and down. It's not the same. It's not reliable. And we're working on a paper with many others to try and figure out what the factors are, why sometimes it goes up and sometimes it goes down. But that's what we found. So this is important data from a long time. But as you can see, I've worked on controlled drainage now since 2004, and it's good. I like to present about it, but I don't think it's going to be a great answer. It's a tool in the toolbox. But we need to look around. If we're really going to find something that's resilient, the problem is it doesn't really store enough water to help through those greater droughts that we're expecting in the future. So what I am excited about, but still there's a lot of questions to be answered, is the idea that why don't we just save the water in some kind of a pond or a reservoir and then not just let it out like a stormwater pond, but actually, oh, here we go, put it back on the crop through irrigation. You can see the great advantage here, right? Because not only are we storing the water, but we're also storing the nitrate and phosphorus in this pond, right? This pond is going to have all the nutrients in it, and they are then going to go back on the field where they're not a problem, not only not a problem downstream, but they're a benefit to the crop. So this kind of a closed loop system is just what, you know, we can hope for. And I think a lot of people here are like environmental engineers, and that's what we try and get in so many systems, right? How can you close your loops? So this is what we hope for, but so many barriers, but that's what we're thinking about. So here is a drawing of the system, and you'll see this through a lot of what the rest of my talk of talking about how we look at this system. In this system, it's got, so the drain flow is coming from the cornfield, it's coming into the pond, you can see that. In this system, it's going back into the field through something called sub-irrigation, which is an uncommon form of irrigation, but it's a possible form. Instead of having a sprinkler system, you're actually pushing water back into the structure, and it'll be actually pushing back into the tile drains. So in places where this works well, it's a super system. It's just not, there aren't that many systems that it can work. So this recycling water idea can work with sub-irrigation, or it can work with sprinkler irrigation, the much more common kind of irrigation. So just because people often think that it somehow means sub-irrigation, I like to mention that. It doesn't matter what kind of irrigation. The point is, instead of out of a well, you've taken your water out of the pond that took the water and nutrients from the drain flow to get that loop. You know.
Yes, you.
Holding questions.
Holding questions. Oh, I'll ask later.
Okay. Okay, there aren't a lot of examples in this because you can guess right away it's a very expensive system. So it's not like this is just waiting and everybody's jumping on it. But there are examples. This is a system in Michigan that some folks there told us about. This is not the farmer's first pond, this is the second. The first one was put in when a road went through, and just like roads everywhere, they needed a borrow pit to get a lot of the soil out to make the embankments for a big road. So then he had a pond, and he started thinking, what can I do? And so he started using it for this. In Michigan, they actually have another law that makes this makes it economical in places where it wouldn't, which is that you can't withdraw groundwater at a rate faster than the streams can recharge. There's a whole process there. And this is in an area where it did limit their amount of the rate that they could withdraw from the well. So the pond really made it possible for him to both capture the drainage and deal with that. So there are several systems in Michigan. What people need to understand is these are not just a little backyard pond, but they're big. This one, for example, that was just getting dug was 20 feet deep. These are very large ponds. And I just got these photos from an engineer in Manitoba. So these are some of the best photos I think I've seen of how this would really need to work. So these are not necessarily highly ecological, as you can see, but that's one of our questions, that if we were able to get more ponds or reservoirs in the landscape, are there some design considerations that could be included to make multiple benefits, right? Also have benefits for wildlife. And one thing we've learned so far is that the ponds, which will probably go down in the summer, right, because the water is being used, they wouldn't be the greatest for like fish, but they can be really excellent for amphibians. Right, because amphibians, they don't need water in the late summer. So that's what we're hoping to get more wildlife kind of people working on this too, and what kind of design considerations would add that. So here's another one he sent, but I thought these were, these are very large systems, and you just see that. Other ones that I visited are research sites. The only published ones are in Ontario. These are both from Ontario. In Missouri, somebody has published several things on recycling the water using for irrigation. Missouri, you may know, has very shallow soils, and so irrigation is very beneficial, even though they also need drainage. And in Ohio, they had a system where they drained into a wetland and then into a pond and then recycled it, and they published some of that. But there's lots of research questions. So if any of you are looking for research questions, I think these are great. They're great because we really haven't quantified the potential benefits. Right, it's common sense that you can see there would be benefits, right? But how much in comparison to how much it costs? So what we're trying to get at is how much crop yield benefits and how much water quality benefits could we get? Just like controlled drainage, there's two types of benefits, and to get an idea of how practical this is, we need to quantify both of them. So this is what we're working on. Looking at the water balance in a drainage water recycling system. So it's a pretty, it's really just a water balance model that we're working on so far. We have daily drain flow going into the pond, and this is a given. We're not predicting this. You could use a modeled or measured drain flow, and then we keep track of the soil, crop water conditions, and the water level inside. So I can go through those. The basic system is this. We've got the field, and we've got its soil water balance and irrigation, and then we've got the pond, and we've got its water level, right? So this one, we looked at more of the profile level. So if anybody's interested in the irrigation details, we can talk about it, but most of us don't work it. What I'm going to show you the pond water balance and the soil water balance, and then a little bit about the irrigation that links the two. So first is the storage reservoir or the pond. If we look at that, there's two inputs, which are the drain flow in and the precipitation. And drain flow, if you haven't seen the time series of this, is very choppy. There's not like base flow. It flows for a few days and then it stops typically. So this is our measured drain flow data set from the Davis Purdue Ag Center list that I just showed you. And then the outputs are from the pond are evaporation, seepage, and irrigation, right? So we can, here's evaporation for example. So we can simulate any of those, right? So that's keeping track of the pond or the storage reservoir, which is simple water balance. In the soil or the field, we've got also the precipitation. Now irrigation is an input instead of an output from the pond. Runoff is, one loss pathway, and obviously ET is the other big loss pathway. So that we can keep track of that soil water balance. And then irrigation, I'll just tell you in principle, we're learning that the methods that are used in most irrigated areas don't make that much sense here in our poorly drained soil because we don't immediately drain to field capacity, which is the assumption in all the irrigation ponds. But still, we do go through this and use typical irrigation strategies with the total available water and readily available water. And so then we're keeping track of all those, and as water is added to the pond, if there's room for it, it's captured in the pond, but they're very much limited by the size of the pond or the reservoir. How big can you make it? How big can you afford to make it, right? So you're going to have a lot of overflow too. When water, you could capture it if you had space for it, but it's going to end up downstream anyway. So it's trying to balance those. Oops, sorry. Okay, so I'm going to give you an example of using the data, the drainage data from the Davis Purdue Ag Center, where we were collecting data for a different purpose, which was controlled data, controlled drainage. And so this is again what the field looks like, but we're using measured drain flow, on-site climate, and water quality. There's no pond here. But this is what we need to do, right? Because there just aren't very many ponds. So we're simulating what would happen if you put them there. And the way, just to make it realistic for people, we're taking an 80-acre or 32-hectare field and using different portions of it for the pond or the reservoir. 2% of the area, 4%, 6%, 8%, and up to 10%, which most people think, whoa, I would never take 10% of my field out. But in Ontario, for example, he's shown a crop yield benefit of way more than 10%, right? So there is the possibility that you could make it up through the crop yield benefits. And in this case, we're having an average depth of 3 meters. So basically, just running through what I just showed you, the amount of irrigation that we can apply is very limited when we have the small ponds, right? So this is the small pond, it's only 2% of the field area. And this is the large pond, that's 10%. And this is how much irrigation we would put on if we had unlimited water supply, like we had wells, right? So you could just keep pumping. And so by the time we get up to a pond that's 10% of the field area, we're almost unlimited. So that's good. As we go down, we're very limited. So at least this gives us some numbers, right? I wouldn't stand behind these and say this is the right numbers in too many places, but we're looking at sensitivity analysis. We're kind of in that stage right now. So the applied irrigation looks something like this. And then what we really care about, the public benefits, water quality, is first of all, the amount of flow that can be discharged. Oh, and we're looking at a 30-year data set. So the box plots are kind of standard statistics of a 30-year data set. If we had the large 10% of the field, we would be able to capture, 200 millimeters of the flow. It's not flow exactly that we care about. What we care about is the captured nitrate, and this is nitrate N, load in kilograms. So this is the number that solves hypoxia in the Gulf of Mexico, right? Is how much can we capture? And of course, it gets higher the bigger the pond, but we haven't brought economics into here, but obviously they cost a lot more too. The cost is going up in the same way. So that would be some kind of a balance. The 6% field we found has, the capture was 12 kilograms per hectare, which comes out to 45% of the nitrate load. So again, if you remember the hypoxia task force, the state nutrient reduction strategies are 45%. So this one, we can more start to show that with a practice like this, you could get to the 45% reduction and beyond. Obviously, you're taking some land out of production. You can't do it without that. But as the public thinks about what practices can be supported moving forward, this one has a lot of promise. It's just economics, and obviously the economics are there. So we feel like there's a lot more to do, but this starts to give us a clue of how much we can expect. So that's the mission of this large project that we call Transforming Drainage. We were fortunate to receive a $5 million grant from USDA NIFA 3 years ago. We're just starting our 4th year. I'm the leader, but as everybody says, don't you have a lot of money? He said, no, I don't have a lot of money because all these other people are part of it. But we have a great team. Everybody has part of the funding. And what this allows us to do is put many sites together. And that's really been our emphasis, and it's just been so exciting. We're not only taking, the money didn't just fund new research, but it went back to places that people have collected data on drainage even 10 years ago, 20 years ago. Some of it is more than 20 years old. But it's so valuable, but nobody can afford to take the time to make it valuable to others. So we put a good chunk of it in just for a data manager who is at Iowa State, and get it, time to spend with all these people who have data somewhere in their file drawers, and sort of before the days of really careful file management where like NSF or whoever made you have a data plan, right? The data is there. So some of these are new sites, and many are historic. So this just is an example of the one in Missouri. We've tried to pull together key information, so there's good metadata in this data set, maps that show exactly how each of these run, because with these sites, they're not just plots, right? They're all fields, they're big, so people have to understand what's being measured. So we've tried to do that. That's just for the Missouri site where he's been doing drainage water recycling for a long time. And we have, at this point, 186 site years of data. I don't know, sometimes that doesn't sound like a lot, but I think it's really a lot, because many research projects only go for 3 years, 4 years, 5 years. So I think there's 35 sites that had data of a high enough quality, and most importantly, we're willing to share. So it is being put in a common database, and then people we have like agreements on publishing, so that if you share your data, you have to include the other people whose data you're including. And we spend a lot of time on that kind of thing. But we're really trying to get a network where people have shared their data. So each of these sites has some kind of data with one of the drainage storage practices. So this is, you can see, this is Davis Purdue Ag Center, if you remember my graph there. And what we're trying to do now is, how do we synthesize this across sites, right? Because everybody's different, and it wasn't laid out to be an experiment that way. But this is the great challenge, right? A lot of big data questions. You're working with data that wasn't collected for a common purpose. Can we use it for a common purpose? So that's the biggest and most important component of this Transforming Drainage project is the field research. We're then working on synthesis and modeling. I didn't write here, but most of the modeling is with DrainMod, led by Mohammed Yusuf and his team in North Carolina. We also have variable infiltration capacity modeling, or VIC, that's providing some data that we can use in the tools also. We're taking the model output and putting it on tools, which I'm going to end with. And then we do extension and education because it's an integrated grant. And then, actually, we have another objective which draws us all together to say it doesn't matter if we just do all these things ourselves. We've got to make sure that people who can use them hear about them and give us feedback. So we have a lot of interaction with the drainage network. If anybody is interested in working on drainage and wants to know more about the network, be happy to talk about it. So one of the things we're working on is a computerized tool that would do just what I showed you. I'm calling it the Drainage Water Recycling Evaluation Tool, unless we can figure out an acronym that pronounces better than DWARET, but that's what we have. So we've got the input screen. You put in your range of storage volume. So what you're trying to do is say, how could I choose what size storage to put in? So if I go all the way from, I did it in acre feet because to me that's really easy to picture. How many acres, how many feet? So maybe 10 acre feet would be a small one, be 1 acre, 10 feet deep, up to 100 acre feet. What kind of results am I going to get? You put in some kind of a daily drain flow. This is measured, but if you don't have it, then we've used this simulation modeling using VIC, and you can pick out any location and get a simulated 30-year drain flow so that we can feed it in. You put in your inputs about soil and irrigation, and then you get a number of outputs, but these are the simplest ones. So what we're trying to do is make it accessible to drainage contractors and farmers who people keep telling me don't want to look at box plots. I say, well, how could you not want to look at box plots? What's better than a box plot? But okay, I've been convinced. So what we're doing now is putting the mean and plus or minus the standard deviation, again, over a 30-year drain flow. So it would give people an idea of how much irrigation you can usually add. So these are the different pond sizes, right? So obviously a next step, a future step, would be to put some cost in it, but we're trying to figure out how to standardize cost because, you know, there's just more cost out there, but how much more? Oh, sorry. Okay, so this is the annual captured flow, and people, for the most part, don't care about captured flow, but what it is proportional, very close to the amount of nitrate and phosphorus that's captured, and that's what we care about. That's what the public cares about. And then the private benefits would be here. What we don't have is how much crop yield benefit you will get from, let's say, 6.5 inches of irrigation, because that varies too, but we're thinking about how to make that more useful. So that's one of the tools we're working on. The other one, and I want to call out Ruth Book here, who got NRCS to work on this one, is looking at the suitability for controlled drainage, because that's another question people have is, where can I put controlled drainage? So folks at NRCS have looked at soils. This is not a very great, there's a big screen capture and I put it down, but anyway, Illinois is in here, and so you can see there's a lot of area that's suitable. This is a screen capture, but it is a web-based, so a GIS web app, so you can zoom into an individual field. And so finally, so we've got tools, you've seen the research site, and finally I'll just say, we're doing a lot of extension and engagement. I don't know if this helps you, but just to know what we are, we've got different publications, and we do field days events throughout the region. I will just say at this point that we have this is a brand new publication. This isn't directly from our project, but I was just working with folks at here at the Ag and Biological Engineering Department, and actually Soil Crop Sciences, Laura Christensen is the lead on this, and picked up my 5,000 copies of this. So I said, okay, I'll just distribute it here. But this is what we in Extension, try and put out. So this is not just the drainage storage practices, but it's all the kinds of practices that people can put on drain land to reduce nitrate loads. So it goes to the agronomic practices, changes to the drainage system, and edge of field practices like bioreactors. So feel free to pick one up as you leave or now. But we do a lot of that. We also work a lot with the private sector. And fortunately, the private sector has been very interested in supporting us with these drainage practices. So the Drainage Contractor magazine we're in, and Iowa soybeans. So it's been a really fun thing about this project. So again, just to end, the vision, this is what the point of why we call ourselves transforming drainage, is that long-term, it's not going to happen tomorrow, but long-term agricultural drainage won't just focus on getting rid of the water as fast as we can, but we'll actually be thinking about water storage and actually recycling. So when we have the nutrients coming out, what we can hope to see is that they go back up onto the field, where not only do they cease to cause problems downstream, but they actually enrich our crops. So that's the vision, and be glad to answer questions and talk more about how to achieve that vision. Thanks.
Go ahead and take questions.
Yeah.
Up here in front.
That specialized irrigation system in the early part of your talk you mentioned, that involves getting the water directly to the roots, not spraying it on the surface, so you're not getting much evaporation at all. Is that the good thing about it?
That is all true, but the good thing about it is you don't have to buy an additional system. So farmers already have the tile drains, so I think, can I use those same pipes? And you can, it's just that the spacing needs to be narrower to make this efficient, because you can get water into the pipes faster than you can get it back out. But their thinking is you don't have to buy anything additional, whereas a center pivot system might cost I don't know, $50,000 to $100,000. So you're saving the cost of a system. It actually isn't ideal because tile drains are typically at 3 feet, and where you want it in the roots ideally is 1 feet. So you're actually applying water lower than what you want.
So, can you adapt the old tiling system for this kind of irrigation system, or do you have to dig it all up and replace it?
No, you can adapt it, but you would probably, what they're often doing is adding additional tiles so that it's instead of having maybe 40-foot spacing, you might go down to 20-foot spacing. So it's quite narrow and it only works in soils that are permeable enough that the water you're adding into the tiles has a chance to flow laterally to provide water for the entire field. So there are a lot of drawbacks, but in the few soils that are really permeable over a really impermeable soil, it works great. But there aren't that many soils that have the right properties. That's why.
Have you measured the nitrate and phosphorus concentrations in the water that are in these reservoirs going back onto the field, so you could see if farmers could actually reduce fertilizer load then, or how much is going back on the field?
Okay, so first of all, there aren't many measurements because there aren't many systems. They're a little hypothetical except for these, but yes, they have. And it's basically close to the same as what goes in, right? We've measured a lot of drain flow, and there isn't a lot of cycling in the pond. There's a little, so that it's a little less than is going in, but it's almost the same. But absolutely, farmers could reduce the nutrient balance. The agronomists always hesitate to say they can reduce it with controlled drains. The first practice I talked about. In theory, maybe there's some water there that wouldn't be lost, but we're too uncertain. So they really can't reduce it. But with the drainage water recycling, there's really no reason, once we get things more quantified, that they couldn't, because it's coming back on. So we've written many proposals. I just heard from new systems where some new systems are going in, which is very exciting, and hope over future years we'll have a lot more data. And that's certainly a key question that people have, is how much you can reduce your application.
I don't think I heard you mention no-till farming. What effects are that?
Well, no-till farming does not have a lot of influence on nutrient losses at all, unless you have erosion and are stopping erosion. In our flat fields, most of the water is moving down to the tiles, whether it's no-till or tillage. Where the no-till can help is better soil health. So I did way at the beginning talk about soil health. If it can help build up the organic carbon in the soil, it would be a really long time to have a lot of influence on organic carbon just from no-till. But if you combine it with cover crops, then that can speed along. You've got growing material throughout the year. So cover crops would have much more influence than no-till does. But it's not negative. It's just that either way, the water is typically going to infiltrate and go through the tiles. Yes.
Other than economics, what's public perception been of this? Are there other obstacles?
Okay, economics. Other than economics, it's quite a hypothetical, isn't it? Well, one thing we've been talking with some farmers about is that they keep bringing up how they just love to have more land. And if you deal with farmers, you probably know this, right? Everybody wants to farm more. They're competing to rent land. They own what they own. They're trying to get more, and they're competing for rental agreements. So it seems like just psychologically, the idea of taking any land out of production is heartbreaking to them. So even if you're going to have more corn out of less land, that doesn't seem to be necessarily a positive. They love to have land. It's not anything I can say quantitatively, although we're working with a social scientist who's going to be asking more about the influence. Well, one of the questions is the influence of crop insurance and other policies on people not adopting climate resilient practices like this. There's just there's the resistance of us doing anything that might be admitting that the climate is changing, and that therefore you need more resilient practices. There's those kind of barriers. There could be, I think we don't have enough people thinking about what possible harms ecologically could come about. So more ecologists could certainly help. The ecologist that's on our advisory team that we talk with regularly says, well, wherever there's water, you're going to get aquatic life. So that's good. But, is there could it possibly be harmful to them? I don't know. So it's going to take land out of production is really the biggest.
So with the nutrient loss reduction strategies and maybe regulations coming, that might push this if regulations come that the nutrients can't go into by river down to the Gulf of Mexico?
I think that this is one of the practices that is the most certain to reduce nutrients. But we have the least data, but nobody can think of a reason why it wouldn't work, right? We just don't have a lot of data because it's expensive to put in. But other practices rely on certain conditions. Bioreactors, if you know what those are, these are where they're adding wood chips and water goes through them, but you have to have certain conditions to have denitrification or else you've done nothing, right? So there's a lot of ifs there. This practice is simply a question of sizing. How big of a pond can you get and how much will it catch? So, well, even on this publication, if you pick it up, we've got the nutrient load reductions that are in the Iowa and Illinois, strategies. I think the one is Iowa. They're close to what is assumed for these practices, and drainage water recycling is not on there because there isn't a lot of data that you can use to show it. But I think that there's really little doubt that it would be. But obviously, it's a very pressing need to have the data. So we're really eager to look at that. And whether some kind of policy changes could promote this, it's important that the policy changes be flexible enough to say you get paid or whatever it is for reductions in load, not to put a certain practice in, right? So if in that case, this practice would hold up very well because I think the reductions will be strong. So it's those two things coming together that we think, even though I can't say this practice is economically beneficial right now, it really wouldn't be. But if the public joins in because of the nutrient load reduction benefits and pays for part of it, and as the climate continues to become more extreme, right, so that more and more of our water is coming in the spring when we don't want it and less in the summer, then there will be a push from the other side. More and more people are thinking about irrigation already. So those two things will work together in the same direction to say we need to think about storage. And we can certainly be very flexible about where in the landscape the storage can go. Farmers, if given incentives, can be very creative about figuring out places to do this. So once the economics are there, I think they'll find places to do it.
It's a great talk. So you mentioned that you're using pond or reservoirs, collect the water in the spring and irrigation in the summer. So I think it's very good idea, very good. I just wondering, did you think about the water quality for irrigation? Because you collect water in the spring, because you have high nutrients. So also maybe have another contaminants during a couple months, they will generate, like, for example, like algae bloom, for the algae toxin. So that's why the water quality, in the summer you want irrigation. Do you think about the water quality?
Yeah, we do to some extent. And so here's how we think through it. One, there will certainly be algae, right? These are ponds that are specifically full of nutrients, right? So that's the only problem I see with the algae, if it goes back on the field, it's still the nutrients are there, but would it clog the sprinkler heads? Right, so that's an argument sort of against sprinkler irrigation, but it's not an argument against putting the algae-filled water back on the field. I don't think that's a problem. The problems are the other things, and one thing people raise is could the herbicides that are in the water be bad? Well, so this would be a problem if you put it back on a different field. But if you've got a cornfield, so you use corn herbicides, you put the water back on corn, that's not going to cause a problem either. Remember, these are contaminants in the wrong place. If it goes downstream, it's a contaminant. If it goes back on the field, that's something people are paying a lot of money to have more of. So it's not exactly a contaminant. You could have pharmaceutical kind of contaminants from manure, for example, but again, if it went back on the same field, it's only adding back to where it was. But you could have a problem if manure was spread, it went downstream, and you applied on a different field where it wasn't there. Sometimes people jump to the conclusion that we're talking about using city retention ponds, kind of, and then you would have very different contaminants because you have the, metals and whatever else there is. So that would be a different issue. And I didn't say it here, but often I do say that, that we've had changes in the landscape before. 30 years ago, people, you know, Walmart or whoever could just go in and build a parking lot and just build it, right? But now that's unthinkable. We all know if somebody paves a whole lot of land, they have to put in a retention pond, right? So that's a big change that we've seen. So I often use that as an example, and then people start thinking, oh, she's talking about using, you know, Walmart's retention pond on the field, which would certainly introduce other contaminants. It also, another water quality issue, and I've just been talking with a public health person about this because they're studying non-traditional uses, is if you used it on food crops like vegetables, then you have many more water quality issues. What you put on corn, which, as I'm sure you know, is primarily used for two purposes, one ethanol and one you know, livestock food, neither of these have strong public health implications of the water quality. So that's a few of the thoughts, but I'm sure there are many more questions that haven't been addressed, and maybe people get some ideas on ones that can be addressed here.
Would this be a practice that might be put in place more in places like Nebraska or something? Out there, because, you know, the groundwater is that, would they be more inclined to maybe put in these ponds for that?
No, because they don't have the excess water problem, right? In the places where the groundwater is, they're not excess in the spring either. There's a few places where they do have excess water in the spring, but for the most part, they don't have our poorly drained soils, right? So what's unique here, why we've got such a drainage problem, is we've got glacial landscapes that laid down a very impermeable layer, 6 feet below the surface. It varies, but basically we've got a real impermeable layer most of the time, and they don't have that in Nebraska. So you don't have something that's holding the water up and causing there to be drain flow. Their excess water, when they have it, goes straight down. So they have to be using wells. That's why. So it is a tough sell though here, because Illinois doesn't need that much irrigation, but yet there are probably subtle benefits.
Did you have one up front?
Is there any issue in the ponds of the nutrients being concentrated at the bottom as opposed to being suspended in the water uniformly through the water column?
I don't know. That would be something to look at in the future. I don't know that there's a good reason with nitrate for it to do that. It just is going to stay dissolved, right, anywhere. So, and I don't know if it would be a problem, right? With a phosphorus, it wouldn't be a terrible problem to stay at the bottom. And we wouldn't get the benefit back onto the crop. So that's what we keep asking these questions of, is there something that would be harmful going on the crop? If not, then great. Put back on the crop.
We have time for one more question.
And I will ask a question. So you've alluded a little bit to the cost trade-offs, and I'm just curious if you've done any type of initial analysis where you said, okay, do you get your 2 or 3% yield increase, and you compare that to the cost of building a pond, does that take 5 years to pay off, or does that take 50 years to pay off, or does it never pay off?
We haven't done that.
Okay.
We do have some, rough cost estimates that people are using, but we haven't put it in those terms. But what I do say to everybody is it's going to be a long time before it's going to be cost effective without the public participating. But I don't think it needs to be completely paid for itself, because we spend billions as taxpayers each year for practices to promote water quality. Maybe that's not each year, not sure how anyway, we have spent billions over 10 years. So there's a lot of public money that's going to practices like these. And so that should be part of the equation. But what we need to do is still the analysis you suggest. We need to put it together with even some assumptions about public funding, a part of it, and the private benefits. So that's coming. Once we figure out how much water we can hold and how much irrigation we can get out of it, that would be a huge step. So that's good. And on future research, then it always keeps us looking to the future, right? Thank you.
Thanks. Jane will be